Elan is able to detect different surfaces and different gait characteristics. It's very important that the ankle and the prosthesis can adapt to these different requirements. When an amputee will encounter an incline, it's very important that we do everything we can to effectively assist that action going up the hill, to preserve that momentum.
Elan can assist the gait by controlling the amount of energy going in and out of the springs. When the heel strikes an incline, the plantar flexion resistance increases, encouraging increased energy uptake in the heel spring. This energy is released at the moment propulsion is needed to assist the forward movement. As the body's centre of mass moves forward, the dorsiflexion resistance is reduced, assisting forward momentum and propulsion.
The human body has a natural speed of walking which is determined by how efficient the muscles can convert calories and energy into actual movements. And the body wants to move at a specific speed to ensure that this optimum speed and control is preserved.
The resistances at heel, toe and ankle are controlled independently to ensure that the body moves across terrain most effectively. On level terrain, sensor settings affect heel spring stiffness and variable resistance in the ankle, and also affects the timing of resistance and energy release in the toe spring. Should stairs or other terrain be encountered, then the Elan will change to a suitable program mode for smooth transition, and adapt again on regaining level ground. The Elan has a speed boost for transtibial users, which enhances the dorsiflexion characteristics for faster rollover as the walking speed increases.
When a downslope is encountered, the propulsion momentum isn't what's required. What's required is a safe, stable transition of body weight across the ankle. And there'll be a natural tendency to walk down the ramp at the speed where the gait would try and run away with that person.
When the foot encounters a downward slope, the plantar flexion resistance decreases so that the foot moves quickly and safely to foot flat. Dorsiflexion resistance increases to support the centre of mass and add a braking effect. This also assists knee extension for safe and controlled descent. A variety of sensors measure weight transfer speed and knee angle to determine the knee security requirements. The knee is intelligent because an onboard microprocessor takes information from the sensors to anticipate support and speed requirements. The microprocessor is programmed with 8,000 lines of code that uses the data from a whole range of amputees. Using this data, the processor instantly activates a unique combination of hydraulic and pneumatic actuators. The hydraulics provide sensitive stance control by varying the resistance to knee flexion. The pneumatics provide a very wide range of speed control by encouraging knee extension at an appropriate rate, powered by the compressed air in the chamber. As you descend the first step of the stair, the hydraulic resistance offers an appropriate yield level to stiffen the knee. The pneumatics assist the knee to extend ready for the next step.
Okay, so we're going to do multi-speed walking.
The clinician activates the programming phase of the knee with a clear set of instructions.
Push the minus button.
The amputee walks around in their selected environment so that the knee can adapt to their preferred walking style and the environment. The clinician is kept informed of the status of the knee by colour-coded LEDs on the knee control centre. The Echelon VT foot comprises a hydraulic ankle with an axial shock and rotation unit and E-carbon foot springs. The motion of the ankle ensures smooth foot compliance on ramps and rough ground so that the foot moves to foot flat for optimum balance at all times. It encourages good postural symmetry. The titanium spring-controlled axial compression and rotation reduces shear forces at the socket interface and cushions the body throughout activities. The E-carbon foot springs respond energetically to each stride and provide medial and lateral rotation of the foot so that the foot remains comfortable, safe and secure on cambers and stony surfaces. As the heel strikes the ground, the heel spring compresses and the hydraulic ankle rotates into plantar flexion, enabling whole foot contact with the ground. Comfort is maintained as the axial spring provides cushioning. The foot encourages the transfer of body weight by extension of the heel spring and forward movement of the ankle. Axial compression ensures comfort and reduction of shear forces. In mid-stance, body mass transfers smoothly onto the forefoot as the hydraulic unit controls tibial progression, and comfort is maintained throughout by the rotation and compression of the axial spring. The toe dorsiflexes and the toe spring compresses to ensure weight transfer onto the forefoot, and then the E-carbon toe spring and the axial spring decompress for an energetic toe off. During swing phase, the toe remains dorsiflexed to assist toe clearance.
The second source of stability is here achieved through what we call swing and stance hydraulic yielding control system. The effort the amputee has to apply in extending the leg to deactivate the high resistance of the hydraulic now can be assisted by this leverage, so effectively it amplifies. So by putting a little force, that force now being a lot less, which has meant the amputee's reaction has been, this is a lot more efficient, there's a lot less effort involved in activation, therefore they can do a lot more with it.
The Elite Blade's dynamic pylon, constructed from an advanced E-carbon laminate, gives the wearer a lively sense of tibial progression during gait. This feature, combined with the V-shaped independent heel spring, offers a great running response and relaxed and comfortable walking. During loading, the deflection of the pylon minimises shock load transmission to the skin interface, proximal joints and lower back. The result is a low-weight foot with high-energy spring action. The blade adapts well to tough terrain because the deflection of the toe pylon assists on inclines. The subsequent release of stored energy from the compressed spring helps propel the wearer forward into the next step. When going downhill, the V-shaped heel spring deflects to absorb shock and to smooth progression. The split toe ensures inversion and eversion compliance, so that the foot transfers comfortably to foot flat.
We use the gait analysis instruments to understand the effect that prosthesis has on posture. And what we found is that we can produce a much more natural control of posture when you use Echelon. Suddenly, with the introduction of hydraulics, it became clear that actually with the correct alignment, we then would be able to facilitate this natural adaptive behaviour. The hydraulics will then move to self-align to facilitate this natural posture.
A conventional foot forces the leg to one position. This can be optimised for walking on the flat, but it would not adapt to an incline and will force an unnatural posture and so stress the rest of the body. We can see with this conventional foot that the body is swaying from the hip to maintain balance on this incline. But the posture is straight with Echelon. This translates into easier and stress-free walking on a variety of slopes.
The mechanical design team and hydraulic design team had an extraordinary challenge in developing this foot because it's extraordinarily difficult to design a structure that mimics the way the natural body does. but can also withstand repetitively all the impact loads that we've seen in natural food.